What is our all right, are we good to go? All right, we're gonna get this shindig going. Cool. Well, thanks everybody for showing up. I appreciate it. Honestly, thanks a little bit for running late because I just got here. So awesome. Andy, you want to come talk? Sure. Andy is from Blue Canopy. They are happily sponsoring us.
Hi, this is Terry. She's also from Blue Canopy. So we're Blue Canopy. We love to bring pizza and beer every month for OWASP. And thanks all for coming. We're a IT consulting company based in Reston. About 400 people or so. We are about half development, big data analysis, and half cybersecurity. So, and this is Cherry. She's our wonderful crackerjack lead recruiter. But we don't say anything about that.
No, we don't. But we are going to host the social event too in December, so we'd love to see you guys out there. Cool.
Perfect. You know where we're at?
Yeah, we're gonna find the date. So probably the first week, second week of December.
Yeah, December 9th we're shooting for.
Yeah.
And we'll post it to the meetup group. We'll finalize it this week and post it.
All right.
Yeah, so it's a lot of fun. Bring friends. So we'll see you guys out there.
Wings and beer and all that good stuff.
Yeah.
All right. Working weekends.
Thank
All right.
you.
So we also want to thank Uber offices for hosting us. They do this free of charge every month because they like us or something. It's awesome. So if you want good space to work in, temporary office space, whatever else, look at Uber offices. They're pretty good. See, bathroom Wi-Fi. If you don't know, Wi-Fi is that little thing right up there. Internet ! $3. Kind of lie. It's totally safe. And if you need to use the restroom, you go out to the front desk. There's some water bottles with the little key fobs on them, and the restrooms are out by the elevators. Let's see here. Other business. We are the local DC chapter. OWASP has a lot of different chapters all around the world. They run a lot of different projects. They have a lot of great resources up on the web. OWASP.org, check it out. It's totally worth it. Thank you for being here. As folks from Blue Canopy mentioned, our next event is going to be a social event joint with the Northern Virginia group in Arlington on or around December 9th. We're working that out. It will not be stand up here and listen to people talk. It will be sit with people, learn, stand with people, and drink or drink water or talk or whatever. It's a lot of fun. So you should show up. Let's see. The last thing on the docket, which the three of us and the folks from Nova have been working on for a few months now, and we're really, really happy about, is that OWASP AppSec USA. The big conference that AppSec puts on a yearly basis. It's a rotating conference. It goes all around the nation. It's going to be here in DC next year. Our chapter, Northern Virginia chapter, are going to be hosting it. So awesome! In the next few weeks, we'll start talking to people about volunteering, getting stuff together. But yeah, put on your calendars, October 11th through the 14th next year at the Renaissance right by Mount Vernon. It is going to be awesome. I'm really excited about it. So, you want to know more about AppSec? Everybody in the world? Well, a lot of people in the world, most of the people in the USA, they're all going to be here next year. It'll be great. So, with that, Dr. Mark Sherman.
Thank you for having me come here. I'm asked to share with you a little bit about one of the things that my group does, which is building the secure coding standards. And we'll take a look at why we're doing that, how we do that, and I'll give you a couple of examples that motivated some of the rules that we worked on so that you get a better feeling for how this whole thing evolves. We'll start with what I view at least as the state of the software, why it is that we're doing these kinds of things to begin with. I suspect that much of this will already be familiar with, that software vulnerabilities are everywhere. And when I did these kinds of talks, what I used to do is before coming, I'd go to the internet and do my favorite search and look for the latest one. And it was at one point fun, PF Chang's or Anthem or whoever it was this week. There was always another one to add to it. I sort of got tired of it. But for this audience, of course, it may be more personal. I don't know about you, but in the crowds that I run around with, this is actually one that has some impact as people get the letter saying the Chinese now know everything about them. But the upshot also is that this stuff is expensive. In particular, this is the Target example. You can't read the fine print. That you're never going to be able to read the big print from the back of the room, so I'll read it to you. On the bottom, it says that over 100 million people were affected by it. On the right, it says that Target lost 50% of roughly 50% of their earnings at that time because of it. And in the lower right, it says that if you look at how much these kinds of things cost, it says about $188 per record, per person that's been affected. You round that to 100, you round that to 100 million people. The Target event was a $10 billion event. Now, not all of that came out of Target's pocket. That was lost business, it was lost goodwill, it was money they had to pay for, watching over your credit scores and all those kinds of things. But the total economic impact was $10 billion. It was about $10 billion. Now, what's frustrating is that we know how to do better. What happened to Target was avoidable by using things that we already know. There's no new research, no new operations, no new techniques that had to be invented in order to prevent what happened to Target. And yet these things still happen. But now it's starting to cause real cash out of people's pockets. So, in particular, Toyota had a similar kind of problem with their software. Anyone read the reports on Toyota? What happened with them? With their brake and accelerator problems? So,
No, that one, or everyone, gas pedal stuff, that one?
Kind of, yes. But there may have been, so the actual code itself is under court seal. You can't actually see that. But there are a lot of reports. It's sort of interesting. So the people who did the reports aren't allowed to say what they did, but they are allowed to disclose that to other people who did summaries of their reports, and that you can get a hold of. And you see all sorts of garbage in there. Well, there's nothing worse than that. So no one can point a smoking gun and say, that's the defect in their particular code. But what you see is, for example, they used one thread that does keep alive, and at the same time also integrates between the brake and the accelerator. Well, when one went wrong, guess what? The watchdog timer that's supposed to keep track of when things go wrong also got stopped. It's just filled with things like that. In this case, it was real money. This is money out of Toyota's pockets. This is over $1 billion on the top they paid to the federal government as a fine. The bottom is $1 billion they paid to people who were hurt. And then, by the way, that particular $1 billion is just for, again, you can't see that, but that's one particular law firm. They still have more settlements that they're trying to work on. So now it's really starting to be cash out of pocket.
Keep going.
Sure, no problem. And what makes it all the more frustrating is that if you fix these early, it's cheap. That if you wait till you find and you put it in operations, just fixing it costs almost 1,000 times more. And the reason why I'm going through all this is not because I think you really need to be convinced, but to do these kinds of activities usually means that you have to spend some time, some effort, perhaps even some money on tools or what have you, in order to do this and to convince the environment that you're in, your boss, your manager, your customer, that this is worthwhile. This provides the kind of financial data that one might use. Am I getting too close to the camera?
Just a little bit, you're good right there.
All right. So in order to explain why even these modest kinds of things that I'm talking about, like the secure coding rules, are a worthwhile investment. So my group actually is focused on how to build secure software. Coding rules is but one element of it. And I have some handouts here. Some of them are on the coding rules, some of them on some of the security design elements. And we actually are having a conference here soon as well. If you want to, you can come and get a whole lot more detail as well. But To build secure software, it's really about the whole life cycle. It's about having the right requirements, and that by requirements means what is the business process you're trying to use, and how many people work in government versus how many people work in government, how many people work in what I call commercial or private sector. Okay, so I'll try to speak both languages at the same time. So you have to look at either the business process or the mission thread in order to understand what you're trying to accomplish. And from that, you then have to figure out what your threats are. How can you be attacked? It turns out that a lot of the problems that people are seeing is because they never were aware that they could be attacked in a particular way. They thought that they were safe. They had physical security or other kinds of isolation, which really weren't true. Then build abuse cases and misuse cases to go along with your use cases. You then do some secure design and architecture. You do some secure coding. We'll get a lot more of that later, into testing, validation, and operations. Now, just to be clear, because my group is part of a larger group that works on cybersecurity at the Software Engineering Institute. There's about 400 of us in cybersecurity within the larger institute. And many times you say cybersecurity, people say, oh, you're talking about encryption. Well, no. Talking about firewalls. Well, no. Talking about viruses and malware. Well, that's not what I'm talking about. They certainly are part of it, but we call that typically security software, as opposed to building secure software. How to make your CRM system less susceptible to attack. How to make your tank software less susceptible to attack. Now, to do that, you have to employ these various kinds of techniques. Within the government, this is frequently called software assurance. If you're not in the government and you say software assurance, people will tell you, yes, they paid Microsoft for all their Office licenses. Now, the sad truth is, as I mentioned, all the things that we're seeing are preventable. We know how to do a lot of this, and these are studies where people looked and said that a fifth of the time, there's no security consideration done up front. 80% of the time, there's no kind of security testing at all as they're building the code. And if you look at the bottom, close to 80% of the teams don't even talk to each other when they are doing some security things. So when they have a requirement, never makes it into design. Someone does some secure coding, they have no idea whether it's relationship to the testers or not. It's all not well done. We could do a whole lot better. And it turns out that you can get to a lot of the problems by doing better coding. Now, there are times when you do that, you may be less efficient. Very simple example, there's a concept called defense in depth. One of the key principles of that is you don't trust your caller. So you validate the parameters coming in. Sounds very good, sounds very conservative. If you're building a piece of software that goes in a car, that goes in a pacemaker, that goes in something that has weight constraints, size constraints, power constraints, you want to squeeze out every instruction. You might say, well, the program that's calling this subroutine, I know the parameters okay, I'm not going to check them. That's sort of the trade-off is, so certainly you know that you could always do so, but then you get into functional requirements. We don't go into it in this particular talk, but there actually have been a lot of studies that show the main cause of a lot of big failures is when old software, with these kinds of assumptions, is put in new kinds of situations. How many people read the Wired Jeep article or saw the 60-minute version? I mean, that is a prime example of what happened there. If you haven't studied the details, basically you had a bunch of CAN systems that had all sorts of interesting things, like turn the wheel. That's actually a shell command buried in the system below. Very nice, very easy to program their automatic parking system, right? You can just say, turn, right, and so on. However, that was done before they had the new Harman infotainment system that had the web interface. No one bothered to put together that once they had that web interface sitting on the same CAN bus, and now they could get through the Harman system into the CAN bus, into the steering system. Surprise, they put it all together. And on top of it all, it was only accessible because Sprint, which provided the communications to all these systems, left open port 666. And so, just query that, you can find out every single car that was in the United States running. But the day after the report came out, Sprint turned off that port. So if you want to try, you can, but it won't work. Point is, you could fix a lot of things by programming. You have to make a decision whether that's really the place to make your investment or not. If you want to do that, we're going to talk to you a little bit about how that might be done. So this is an interesting cartoon. Did anyone else read the XKCD? I don't know if it's pronounced that way or not. So they had a cute cartoon that basically said, you look at code and it's garbage. So you can't read that. I know that since I went to the back room, I know you can't possibly read that, but if you see the slides later, I think we're distributing them.
Yes.
You might be amused by that. But looking at some more data, again, you probably won't be able to read the numbers, so I will read them to you. This is a curve of software that we have evaluated. And the curve is measuring how many weaknesses we found per 1,000 source lines of code, right? Significant source lines of code. That's what the S is the significant lines of code. And what it says here, and I have the best and the worst, and so those are deliberately chosen. The rest are really a sample of programs, just so you can see what kind of the curve looks like. Now, at the very bottom there, it's a really good piece of software, like 0.02 problems, weaknesses that we found in every 1,000 lines of code. However, that thing on the top right is 200 problems every 1,000 lines of code. Think of that. Every 5 lines of code has a problem. Now, it actually wasn't that way. There's usually more than one problem in a line of code, but still the amount is staggering. So, what you're going to do, how are you going to try to deal with this? My opinion is that for security to be accepted as part of how you look at things, it has to be part of the development process. We can give all sorts of magic rules, but if it doesn't fit in the way you're developing software, it's not going to matter. And so one of the areas that we tackle in trying to promote secure software development is how to fit this into Agile. So this is one of the very canonical kinds of Agile charts. And in fact, this is Scrum. My experience that when most of the people say Agile, they mean Scrum or some variant of Scrum. No one does anything in a pure sense. And the point is that you go through this iteration. And you have an iteration, you have a target list of things you want to do. Stories, if you use other kinds of methods, don't call them stories. Your points, sometimes actually use time and dollars, but you use same kind of general idea. You can add security as a very natural adjunct into this whole process. So the first one, what you do, again, I'll have to read this to you. First step is add what I call code hygiene. That's the secure coding rules that we're talking about. Now, if you raise your hand, I'll ask your people, how many people here go and write buffer overflows? Not many people raise. Oh, there you go. Good. The rest of you are locked. No. But if you ask most people, are you good C programmers? They will say yes. Now, it turns out that there are what I call gotchas when you're programming in C that even experienced programmers are not aware of. And really what code hygiene about is making sure that people understand some of these areas so that as they build software, they apply them. Again, once learned, this is not an impact into how you build Agile software. Second thing that you need to do is have secure DevOps. That's nothing more deep than saying that the same way there are various kinds of tools for checking testing and quality and so on, there are cool tools for checking security and for evaluating code. It should just be built into the same automation system. It runs overnight or every hour or every week, whatever the way that you happen to run these kinds of systems, and you get the same kinds of feedback as part of the normal Agile process. Now the third one is a little different. This is called threat modeling. And now this follows the same paradigm, but is a really new kind of addition. How many here are familiar with something called pragmatic marketing? Okay, don't have that one. So in a lot of startups, sort of the marketing adjunct to Agile programming is this concept of pragmatic marketing. What's important here is that it uses personas. It uses views of users, administrators, buyers, and so on as part of the requirements. The product owner represents all of these kinds of personalities as they put together stories. So they have a story for the user, the story for the administrator, the story for the buyer, and so on down the line. What you follow is that same thing, but you added another persona, another, if you like, view that the product owner represents, which we call the persona non grata, the bad guy. This is someone who's inventing stories in some sense you want to avoid, but they get added into the same process. And once you introduce the idea that you want to have this additional view, it really becomes quite natural for people to start generating stories from that point of view as well. Usually you don't bother to think that way, but once you sort of get that place, you say, oh, you know, I might try to do that. You add it to the list, and then it gets prioritized in the stories that you do in every iteration. And then finally, you have to do the risk analysis. As you've collected all of these stories, and you have to decide which ones to do, now you've got, if you like, the bad guy stories in there as well, and you can make a rational decision about what to do. You still might decide that you don't want to do the security things, or you're going to do a couple because some of the other features are more important. But if you make a considered decision, you probably will avoid the really big mistakes, or the high-cost mistakes, and you again make good business decisions about how security should fit into this whole process. So, how do we actually build this? So again, I'm focusing on that very first element, the code hygiene and secure coding standards. So we've developed a variety of standards. Probably our most popular one, which is on top there, is our C and C++ standard. It's been around for many, many years. ISO picked it up, twisted it around, and made it a standard for themselves. The reason why I say they twisted it around is that ISO only builds things that you can form against. They're already defined with the C languages, so I can't write down another standard that says, here's how to use the C language. Instead, they wrote a standard that said, a tool vendor who wants to check for C has to follow these rules, and that's really what the official ISO standard is about. But what are they checking for? They're checking for these rules. We have a Java version of this as well, which has been out for a long time, and we've gotten things like Perl and Python, and we've kicked around a variety of other ones that are sort of in process. Anyone ever buy this book or any of those books? Anybody ever look at the website? Out of curiosity, if we gave it away, if we made it an ebook, would anybody care? Well, it's just something that we're thinking about. So we've got these standards. It's built in some sense by community. So again, since 2006, we've got over 1,500 people who are contributing into a shared wiki by which they offer their views, their experiences. And we also have a newsletter that we send out that gives updates and new views of the rules as they've been developed. So, how do we develop these rules? So, I've got a I do a lot of these kinds of things. I get asked to show up on lots of committees, lots of panels. In fact, yesterday I was on a panel that IBM had. Everybody at a conference out near Dulles on how to build things for the Internet of Things. They had a panel on security and how to do things. And people normally ask, so what's important? What should you do? What are the most important things to focus on? And you see these top 10 articles showing up in blogs and in popular journals and so on. And that sort of represents my view to what a lot of these things are. And you get no sound whatsoever. All right, anyone here see Blazing Saddles? Too young? All right, remember the scene from Blazing Saddles? All right, so that seems to be largely what my opinion is. You get all these experts sitting around a table and we say, what is important to us? I think this is important, I think that's important. And then at the end of the meeting, I said another one. Anyone here from DHS? So, close your ears. So at one DHS sponsored meeting, we did this kind of thing. And again, at the end of the meeting, we wrote down a report and handed it out and declared that that's how the world ought to work. Instead, what we do in building our rules, we try to be a bit more methodical and to the extent we can, data-driven scientific. So for example, the first thing we do is we look at the actual language itself. Most languages, at least that I've seen, when they are written down, contain things that are unspecified and undefined. And we're not talking about here coming up with some creativity of language that was missed. In the standard itself, it says the behavior here is undefined. If you have an integer overflow in C, it says the behavior is undefined. We don't say what's going to happen. Sometimes they say it's unspecified. If you have parameters in a function call, they will all be evaluated, but we're not going to say what order they get evaluated in.
You can look at the language and it will tell you all these different places that are, we call holes in the language. From those holes, we now then apply our creativity and say, gee, how might I exploit that hole, or how might I be caught by that hole as I look at different kinds of implementations. We then also look at code. We look at things that have problems. Research like Verizon and Symantec and Kaspersky and everybody that does cybersecurity has a malware database. And so we have millions and millions and millions of malware examples. And perhaps as importantly, our examples are unique. That is, we don't have a lot of duplicates that we know of. We think that they're unique because we combine them together. And we actually know what's wrong with each one of them. We've done the malware analysis, and so we've tagged them. So we understand them. And then my team itself has looked at over 100 million lines of source code. Some good, some not so good. So we've actually seen the problems that are there. And there's a variety of other databases around of good and bad code. So we look at those and say, gee, what went wrong here? How might have you programmed this differently? We then come up with a proposed rule. We say, okay, we see this hole in the standard. We see that when that occurred in the field, this kind of problem happened. We'll say, this should be the rule. We then basically put together a fast and dirty checker for that rule. And we run that checker on both bad code and good code. And on the bad code, we're looking, did we actually find a problem? And on the good code, did we not raise a false flag? And frequently what happens is we miss on the first mark, and we change the rule a little bit based on that experience, and eventually the rule converges to the best we can get for finding bad code and not tagging good code. Now, I was quite flippant earlier about experts, but there is a lot of experience out there with the people. As I said, we do have 1,600 or so people who are actively engaged with us, and so we take those thoughts into consideration as well. We don't want to say that experience has no value. It does. These are people who've got access to lots of different kinds of systems. And then from that, we then also assign how important a particular aspect is. There are enormous numbers of very obscure kinds of things that can happen in C that may have no impact. You don't see them. No one has an easy way to exploit them, and they're very difficult to fix. So why spend a lot of time on that? So we evaluate each of the things that we find for the severity. What damage could you do if this was used? We examine each one of them for how easy it is to get to that problem. And finally, we say, how hard is it to fix? So if it's hard to fix, it's hard to get to, it's not to have much damage. In the grand scheme of things, that's not really a priority to go fix. So let's take a look at some examples, and I'll try to do this slowly because you're not going to be able to read the charts. So again, for those who are freshmen in high school and haven't started programming yet, or you've been living under a rock for a couple of decades, there's this thing called buffer overflow. That basically means you overwrite an area beyond the target that you shouldn't be allowed to. And that's sort of the graphic example. The last 4 points in red were not part of the target of the copy, and therefore you're writing beyond the end of the buffer. You overflow the buffer. And if you want to know how to really take advantage of it, there's a book that actually talks about how you can smash addresses, how you can change returns, how you can do function point, all sorts of interesting things. I'll leave it as an exercise to the reader to go and actually look at that if you want to know the details of the mechanics. So, how might that actually happen? Consider the following piece of code. And instead, I'll read this because I don't think it's going to be very visible. The first line basically says I have an x, and I'm going to make sure it's positive. So it's less than 0. I set it equal to 0. Now the second line does a calculation with x. It does a shift. It says take some value and shift it 30 bits. So if I have bits, bit 31 is the high, bit 0 is the low. I shift it over. Eventually, only bit 30 is going to be sitting over there. That's sort of the idea. For some reason, they want just that 1 bit. And since this is a positive number, right, 0 or positive, that 31st bit, the very first bit is always going to be 0. And then the next one's going to be 0 or 1. And then you got all sorts of other stuff that's going to be shifted away. That's sort of where we're at. That's point 1. Second point is we have an array. It has 2 elements, at 0, and at 1. So far, so good. So what this particular program segment does, it says take x, add 1 to it, shift it over 30, and then use that to test whether it's the 1 bit or the 0 bit, right? Because you now move that 1 bit all the way over. That's the conditional, 0 or 1. If it's 1, then do an assignment to the first array element, x of 1. If it's 0, do an assignment to the 0th element of the array, x sub 0. So ultimately, all we're doing is we're taking that bit, that's point 30, at place 30, and we're using that 1 or 0 to index into an array. It sounds straightforward. And therefore, if this all is defined and all works, 1 bit, that bit's got to be 0 or 1, the array is 0 and 1, shouldn't be any problem. Now, what happens if in fact x plus, well, before we do that, because that's a defined value, and the standard says you only write defined things, you don't write undefined things, a smart optimizing compiler will look at that and say, there's no reason for me to do the test of what the bit is, and then use the results of the test to index the array, because the calculation is going to be a 0 or a 1, I know that. I can just index the array directly with that calculation. Instead of basically saying, if it's 1, then x of 1 equals something, if it's 0, x of 0 something, I just say x of something equals whatever. Much better optimization, no branch checking, and all sorts of things that compilers like to avoid. Now, what happens if x is in fact the largest positive number? When you add 1 to it, that number becomes 1, 0, 0, 0, 0, all the way out. Right? You've now overflowed the register. When you do a shift and you move those bits down, the last 2 bits are 0, 1. Depending on whether it's a logical or arithmetic shift, you got a 2 or a -2. If the compiler did this optimization of getting rid of the conditional and doing the index directly into the array, now it's going to do an x of 2 or an x of -2. Both obviously buffer overflows of one kind or another. So it looks like everything you did was legitimate, but because of the cleverness of the compiler, you wound up with a buffer overflow. Let's take a look at another example. Say adding integers and pointers. That's the basic way, that's how arrays work in C, right? You take a pointer, you add an integer to it, you dereference it. That's the semantics of pointers in C. And the standard also says that if you've got pointers and you're doing a calculation like this, the result and the original pointer have to be either in the array or point at the very end of the array. Again, that way you can see where the end of the array is. Beyond that, you're not supposed to do the pointers. You're not supposed to go in front of the array, you're not supposed to go beyond the end of the array, just at the end of the array. Okay, so let's say you've got some code, and what this code is, it basically has 3 things. It has a pointer to the beginning of the buffer, pointer to the end of the buffer. That's yours, you control that, you own that. And someone's asking you to make a change to some elements of the array, so they're passing in, if you like, an index. That was a good programmer. You say, I don't trust that index. I'm going to make sure that index is within the bounds of the array. So what might you do? What very likely you do? You take the beginning of the array, you add the index, and you say, does it go beyond the end of the array? If it does, clearly I've got a mistake, I'm not going to do anything. If it doesn't go beyond the end of the array, everything's golden, everything looks good. All right? But let's pretend that value that came in for the index is really big. How big? When you add the pointer, the base of the array, and this new length, it actually wraps around. If it wraps around, what does it look like? It looks less than the pointer. Right? So as a result, when you test it to see whether something was greater than max, well, no, it actually looks less than max. So we're passing in a very big value that overflowed the arithmetic. You actually wound up generating a pointer that's out of bounds, and again, you've got a buffer overflow. Now, if you're a smart programmer, and there are lots of them, you would say, I get it. I understand this wraparound, and I'm going to check for it. So in addition to the add pointer to the length to see if it's greater than max, I'm going to add it and see if adding the length to the pointer wound up with something that's less than the pointer, right? That means I got a buffer overflow. Sorry, I got an integer overflow. So I'm going to check for that. If that's okay, then I can do the regular check and I can go on. If it's not okay, then I've got a bad index. Now, compilers assume that everything is well defined. As we saw, the standard said that when you add the pointer in the integer, it had to fall within the array. If it didn't fall in the array, the language says it's not defined. So the compiler will know, because it understands the rules, the compiler writer understood the language, that pointer plus length will not overflow. That's not allowed by C. So of course, it's a program where you wouldn't write something that's not allowed by C. And therefore, the compiler would say, since I know that's true, and since pointer plus length must be bigger than pointer, because it's not going to overflow, that's ordinary rules of arithmetic, that's always true. I'm going to optimize that away as dead code. I always know it's true. Oops. However, that's a really clever compiler. Most compilers aren't that clever, but most compilers are clever enough to look at another kind of situation that might arise. If you have something like a pointer plus a value, and the same pointer plus another value, think of it in terms of comparing two indexes in an array, it can say I can optimize that relationship between the two of them by just looking at the two lengths, not bothering doing the addition to the pointers. I don't have to go P of 3 and address of P of 3, address of P of 5, and compare the addresses. I can just look at the 3 and 5. Very simple. Well, in this particular case, it looks like that you're okay because it's pointer plus length is being compared to pointer. The compiler says that's a pretty clear pattern. I've seen this. In fact, I routinely do this kind of thing all the time in making canonical expressions. I say I have a pointer plus length and pointer plus 0, right? Same thing. Now I've got this situation where I've got a pointer plus a number and a pointer plus a number. I know I can throw away the pointers. So now I have a comparison. Is length 0? Well, length is an unsigned number, so it's got to be 0 or bigger. And again, it says I know I have the answers to this already, but I'm going to optimize it away. And again, your test to try to see that you had overflow disappeared. So how can you fix this? Well, again, since you control pointer and max, you do the calculation on them and not on length. And again, this is an example of where getting a little more sophisticated in how to apply the language allows you to avoid a problem that could arise later. By the way, I have to be very explicit. I didn't come up with these examples. My team is far more clever than I am. They came up with these. In fact, they came up with dozens more. They have a whole multi-hour presentation because they teach this stuff on class and in some of the programming courses. And if you really want to see tricky stuff, you can invite them down for many, many hours of this kind of stuff. So how does that affect what we do with these cert rules? I explained how we made these rules. Now we also work on how it is that people should learn how to use them. And the way we do that is that in the books that we write and the web pages we put together, again, you can't see this very well, but there is a box in red that says, here is an example of bad code. Bad code that you probably thought was good code because it looks like a natural thing to do. But here's what's wrong with it. And here is the way to write it that avoids whatever this particular problem is. So the idea is to help people understand not just abstract rules like you see in some places, don't write a buffer overflow, but very specific information of this is how you might have coded, and that's not quite right in these circumstances, and here's a better way to go about doing this. And that's what the books and the wikis are all containing. So that's what we've been doing for a decade or so at this point. And again, we continue to refine it. But there are some new things going on with secure coding as well. I thought I'd share some of them so you can see some of the research that's going on here. For example, threading is becoming a recurring topic in the language community, especially around C. There's a couple of different variants that are being considered. And again, we're starting the same process. We went through all the standard. We came up with all the ill-specified elements of that, and therefore starting to generate the places where there will be problems. Frankly, our first goal when we get into this situation is we go back to the standards committee and try to get them to say what the real answer should be rather than saying we're not going to say what the answer is. Because that way, then you don't have to come up with rules to get around problems of different interpretations. and we in fact sit on these standards committees and go at both the national level and the international level. So that's our preferred way of doing things, is to not have to invent new rules. But, so we've done that with working on threads, and C++ just came out with a major revision, and so we just came out with a major revision of about 80 odd of the rules for C++ as well. Sorry. In addition, we've done analysis on multi-threaded programming and synchronization, race conditions, things of that sort, in order to come up with ways that you might be exploited, and therefore ways that you might want to improve what you've got going on, and we'll show you a checker of that later. But it's actually becoming more important as these start now being put into physical cyber physical kinds of system, or mechatronic kind of systems, because those typically have lots and lots of interacting processors, processes, and threads in them that cause a lot of these kinds of conditions. A car, for example, a high-end car can have 80 or more ECUs, electronic control units in them. Each ECU itself can have one or more processors in it. So there's just an awful lot of little computers all talking to each other, and therefore having this kind of control turns out to be important. We're also doing research on how to define secure APIs. As you're building services, you expose them as APIs. In fact, you're basically building little languages. How do you design those so that you don't introduce security elements? And it turns out there are certain elements, certain factors about persistence of storage, ordering of typing of parameters, typed versus untyped parameters, things of that sort, which, again, there are better security practices and less secure practices. As you might imagine, the less secure practices are more flexible, and therefore they sometimes get preferred. But the idea is to uncover the choices so that you make a rational decision. We're not trying to say never do it this way or always do it that way. Now, in the C and C++ thread analysis, we, along with Google, put together a way of tagging threads in C that explains what the dependencies are between them, and then you can automatically check for that to make sure that you don't have the unexpected behavior among the threads. We're doing work with Android. This is now about information flow and intents among Android applications. Everyone, I assume, has heard about problems with like the flashlight program that also sends your entire phone book out over the internet. In some sense, those are kind of easy to find. We are expecting that what you'll see is really collections of programs that if you look at any one of them, they look benign, but they act in concert in order to leak out the kinds of information you want. And so we've built analysis tools that in fact go and look for those different kinds of interactions, so that as programs are brought down from the store into the application, you get to see whether one of these situations is being set up. A big problem with secure coding is legacy code. There are huge amounts of legacy code out there that most people are not going to look at. So we've also done research on how to automatically look for problems and fix the code. That turns out to be a lot harder than you might imagine. There's a couple of simple examples that are there, like don't print a string that comes into you. Print the formatted version of that string, and you basically will get around the various hacks that use that loophole. Now, the reason why you just can't do a global substitute on those kinds of things, or why you can't use existing program transformation tools, are twofold. The first, typical program transformation tools have as a requirement that the semantics of the program do not change. Whatever the program did before, it has to do afterwards. In our case, that's not what we want. We want the program to be different. We want it to not be vulnerable to certain kinds of attacks. So much of the academic literature on program transformation actually doesn't help, because they go out of their way to make sure that we would keep the vulnerabilities as we did any kind of program transformation. Second problem, especially as a practical problem with C, is that most of the program transformations can only work on expanded code. After you've gone through all the macros, other kinds of pre-processing, then you can start doing some smart things about finding things to fix. That's fine, but it then becomes unmaintainable. What you got is what the compiler would like to work on, not what the developer would like to work on. And so our challenge is to make these changes in the unmodified code, the unprocessed code, in order to get rid of the bad things, teach the good things, and it's still meaningful to the developer. Now, how do we get people to adopt secure coding? As I mentioned, we try to integrate it into the Agile process so that it's a little less painful, but you still need to understand it. So we and others, we're not alone, offer courses, and I'll put in the plug. There are little handouts up front about the various kinds of things that we have, and it's at the conference that's coming up. We offer the same thing in Java. Turns out that for C and C++, it's actually more routine than it is for Java. We have what I call the Java 1 workshop, because for C, it's pretty much the latest version of C is what people use. People use Java 6, Java 7, Java 8, they use ME, they use SE, they use EE, and they're all different. And so trying to come up with a single course doesn't seem to be satisfying to anybody. So instead, we basically have a Chinese menu of, okay, you're doing this particular thing, these are the ones that we'll pull out and help you with. You can buy our book, you can read it online, we can show up and give a course. We have the courses online that you can get to if you like, things like edX or those kinds of systems, remote learning. You can do it on the fly. We can sit with your teams. We've done this in some cases where we actually work through your code, show you the problems, and sort of act as mentors in order to help get that going. And basically any kind of process that you would like, we're happy to engage with. Now, that's a very intensive kind of thing. We're also trying to make this part of the working vocabulary of the developer. So we're working with the popular IDE groups, because they're not necessarily vendors, they're like Clang and Firebug, part of Eclipse, in where as part of those tools, it will look for problems with these rules. So as you're typing something in, it will say, gee, I noticed you typed in this kind of stuff. That looks strange. Is that really what you wanted to do? Now, the answer could be yes. As I said, these rules are not absolute in all circumstances. There might be some circumstances that you know it's okay, in which case you can say it's okay, and you don't have to keep checking for it again. Or you can say, oops, I made a mistake, and you can fix it right on the spot. Again, very low cost. And perhaps as important, after you get reminded 2 or 3 or 4 times, you learn what that rule is, and then you behave accordingly. I said we've done it, we've put in some rules for Clang, we've put in some rules for Firebugs. We are committers in those systems. They are working their way through the trees, and eventually you'll see them in Apple's Xcode and so on, but I can't really predict how long that's going to take for that path to follow. We also, as I said, do analysis. We do it for the government, we do it for commercial organizations. Sometimes we do it on open source just for our own research purposes. But if people need to have some of their code analyzed, we certainly can help do that as well and provide feedback. Find if in the collection of code we see the same kinds of mistakes going on over and over and over in an organization, that will provide some insight on where to go first as to what you should do. Again, for those who are in government, as you might have expected, because we do a lot of cybersecurity research as a federally funded research and development center, we have clearances, we have the ability to process code that's classified and all that kind of stuff. So we can do that as well if that's necessary for your environment. If you look in the literature, if you look in the commercial environment, you'll see that there are a variety of tools you could buy. Fortify from HP, Coverity, AppScan, SonarQube, there's 10 or so of these kinds of things that you could buy to go and analyze code. There's 2 issues that we've generally found with these tools. One is they generate a lot of false positives. At least if you want them to be interesting, they generate false positives. You can actually turn the knobs to generate almost no false positives, but then you also get very few checks as well. So you kind of have a little knob that you have to choose. The other issue is that they each have their strengths as to what kind of problems they can find. Things that Fortify will find, Coverity may not find. Things that Coverity finds, SonarQube won't find, and so on. What we have found is that by combining multiple tools together, you can actually get a better productivity. And so we have one piece of environment we call Scale that looks at the outputs of a lot of the tools It throws away irrelevant things, because actually a lot of stuff that comes out of these tools is irrelevant from a security perspective. Might be important for portability, but for security, it's not. We recode them so that you know that it's the same thing that's coming out of both tools, so you don't have two different things. And then we provide it to the analyst, developer, in one uniform pane. So you get to see that, in this particular subroutine, this is what all 5 tools talked about on line 10. And then you can make a decision about line 10, good or bad or change. And the tool will know that you made that decision. And remember, because part of the issue of all these false positives is not that you have to always, is that not only that you can look at them all, but after you make changes to the code and you run the tool again, all these false positives come out again. This time, we remember that you already looked at it, said this doesn't matter, and won't be brought to your attention again. So again, it makes the analyst more efficient. This is what we have today. What we are working, and if you like YouTube, we've got someone showing you how to do this on YouTube. He makes an admirable attempt to keep your attention, but it's kind of hard to watch compilers and get excited about watching compilers, but he tries. Now we've done another step, which actually surprised us when we did the analysis. It turns out that you can use relationships of different tools plus various metadata, change histories, class structures, defect reports, other kinds of metadata, in order to come up with a much better prediction of which diagnostics are real ones and which ones are spurious. So basically, you can use machine learning and other kinds of statistical techniques that say, covariety says yes and HP says no, and this particular module has changed a lot. This particular diagnostic is probably true. Again, we've got a lot of code that we have that we can run this stuff over in order to do the testing, and we've done that. And we have a system, well actually we're in the process of constructing the system. We did some initial tests to make sure that this had some legs, that it had some value. It did, so that's why we're now doing it in a much larger sense. The idea is we run a lot of code through it, put the learning algorithms, the statistical algorithms on it. It generates a view. We then can use that for new systems. And then again, that feeds back in and improves it along the way. So you may feel that some of these tools have limited value, but you can use them in ways that actually provide a lot more value. And we actually see in high risk areas within the government using these kinds of techniques. Of course, there's nothing that works as well as just having another human being look at the code. If you use extreme programming, you probably had experience with that. We do the same kind of thing. Dynamic testing is something that can be done as well. We talked about secure coding, doing static testing. It turns out that penetration testing actually works. You actually punch at things, you learn stuff. Now, we and others have developed tools as well, so if you're doing penetration testing, you may want to look for things that are doing various kinds of fuzzing, kind of machine learning algorithms. That as it probes gets certain kind of responses, it knows how to adjust itself in reaction to those responses in order to, frankly, to try to break the software. This is, everyone knows what a red team is? Okay, red teams also are very good. The red team that we have claims, I don't know this personally, but they're really sharp guys, claim that they have yet to get a system they couldn't break. That's kind of disappointing, but nevertheless, it seems to be true. I will share one of their secrets, however, for your own practical purposes. Almost every image library that's open source out there is vulnerable to a hack. Almost nobody either has the latest version that's been fixed or does the checking themselves. When these guys get a program, the first thing they do is they run an analyzer, see what library is there. They say, oh, that graphical library is in there, I'm done. And they write the report saying your code doesn't work. So, if you're doing graphic stuff, that's a particular place to go look. So, what have we been spending the last hour-ish talking about? Well, I've tried to convince you that this is really about life cycle. You have to know what you're protecting and what you want to do, what you're protecting yourself against, designing the software so that it meets those needs, and then, of course, the actual mechanics, which we spend most of the time on, of how to program. And then when you're all done, doing some testing afterwards to make sure that you feel good about what you've got before you put it in operation. And then finally, when you get into operation, you get into all the other stuff that people usually talk about cybersecurity, your firewalls and your perimeter defenses, and your malware checking, your phish detection, and all those kinds of things. That's all good stuff, but the idea is to try to do better up front so that you don't have to spend as much time and effort in the back. Is there any other questions that people might have? Sure.
Hi, thank you very much. It was a great presentation. My question is, how much of all of this about translates into other languages like Python for Python security? You still use the same cycle and same.
Yes, the method we use is the same. The big difference is the amount of time and effort that we put into it. And we've put an enormous amount of time and effort into C and a lot of time and effort into Java. And that's really been a reflection of our constituency. We are, at the end of the day, we're a Defense Department contractor. And most of the systems written in those environments are most of it too extreme. I mean, the last data I saw, some of the systems was that 35-ish, 40-ish% are C. And in the non-embedded systems, a big fraction is Java. So those are sort of their high points. And so that's where we focus most of our attention. Guys who pay the bills get to make the choice. So if you've got someone who wants to pay us to do Python, we're happy to go do that.
How many lines of new code, or how many lines of new code are written every year? Like so you had some statistics about 80% don't do any kind of. So I was just kind of wondering how many. Oh, okay.
But I do. But I have seen data, and this is a whole other discussion we didn't have here. And I'm curious to see whether this aligns with your experiences. Something like 95% of all systems are not developed; they're assembled, and mostly assembled out of open source software. And about that 75% or more of a typical application comes from these open software components. And the chat, you've heard about Heartbleed, and so you know that those are ones that came into attack. What you may not be aware of is that open source generally is incredibly insecure. That there have been lots of academic probes where someone just went in there and said, "Gee, can I find something?" And basically was shooting fish in a barrel. They had no problems of it. And there are studies done by other companies that say that 25% of the most downloaded used components all have severe vulnerabilities in them. Something like 46 million insecure components are downloaded from the major sites that have these components. I mean, it's pretty scary stuff. And it goes even worse than that because we're really talking about now software supply chain, in where your app server has an HTTP server, which itself has an XML parser in it. And that was generated by a parser generator. And that itself was compiled by the C compiler. Any price along the way, you could have had some bad stuff. And that's just not hypothetical. Does anyone know about Xcode Ghost? So you can actually, there are examples where the tools themselves that generate the programs, that generate the stuff, have been compromised, and then all the stuff that got built with those tools got compromised along the way as well. So, that seems to be more of an issue than how many lines of new code and whether that's done well or not.
Okay, well, thanks.
So how do you compare security between Java and C++? People think Java no pointer, whereas security is true.
So I can tell you that I've seen opinions on both sides. In my opinion, Java is a lot better. The language itself doesn't have some of these things in it. Now it does have with class loaders and things of that sort, it does have its own places where you can go wrong. But a lot of the things that happen here, some of the wacky examples that you don't see in Java because it checks for array indices. And at least it's supposed to check for array indices and not allow that kind of stuff to happen. So at that level, it's I think it's more secure. I've seen other people say, well, yeah, but things like class loaders are so squirrely that you can really do some things that are unexpected and cause some real major damage that way. So the fact that it might be harder or more obscure doesn't mean that it's more secure. Security through obscurity is not considered the right way to approach this. So I've given you my opinion, but I've seen multiples.
Can you do buffer overflow in Java?
You're not supposed to be able to. Again, unless you screw up the class loader, in which case you're now dropping into assembly language and getting underneath the covers, right?
So on that point, so Android based on Java, iOS based on C++. So which one more secure?
Again, my opinion would be Java. C++ is not all that secure. I mean, it's,
So I'm saying compare the mobile, the iOS and iPhone and Android phone. They're one based on C++, one based on Java. So which one more secure?
I think that's really an academic question because especially in the Android environment, people drop into, in both of them, they drop into assembly language to do other kinds of things as well. So you don't stay at that level. Now, what I have been asked, I don't have the answer to, is what about Swift?
Yeah.
And, we took a quick look at it. We have opinions, but they really are at levels of opinions. We haven't done this kind of analysis, which is what you really ought to do in order to come up with an opinion. But we're aware of it, sort of an intellectual curiosity. If you've got if you've got experience with it and some reactions, I'd be curious to hear them. Sure, in the back.
Yeah, you always get a statistic on like, let's say for every 100,000 lines of code, there's 20 plugs in the software.
Yeah.
In your experience, how many of those 20 faults that you find are actually exploitable though? Like, because we have a problem where you can find a bug and it's not like exploitable dynamically through the application or it's like a nested function within the application, you know? Just kind of curious.
So I'll give you two answers. They're both partial answers. So the first answer is when we looked at actual defects, actual problems found in code, about 5% of them were security problems, that means vulnerabilities, not finding artifacts in the source code which you said, gee, is this right or wrong? I mean, these are things that went wrong. So if you want to say, about a ratio of 20 to 1, then that gives you a kind of feel for what you might be expecting. If you're seeing 100 defects in your code, you're probably seeing 5 security things that are going on in the code. That's just an empirical measurement that we did when we looked at lots of different code. So that's one answer. The second answer, which probably aligns with your expectations, is that a huge percentage, and the study that I didn't give a number, so I can't give you that number, but it was a very large percentage of security problems arise when old code is used in new code. That when a new system ships, the data show that the defects, the things that are wrong with the quality or function, are in the new stuff that was written. The security defects, the things that cause vulnerability, are all in the old code that was put in there. And I think that goes back to the discussion we had before, that when people write code, they make it against certain kinds of assumptions about how it will be used. It gets placed in a new environment, those assumptions are no longer true. The Jeep being one of the most extreme examples. I have other examples of where steel mills, the furnaces and steel mills were compromised exactly through that kind of way. The SCADA system used to be just on the floor plant, got connected to the ERP system, got connected to the CRM system, got connected to a web front end for the customers to use. A hacker got in and destroyed the steel, destroyed the furnaces. So, it's those kinds of scenarios seem to happen a lot. And that's why I comment it's a life cycle, because you need to know what your operational environment is, what your threats are. And if you change what your threats are, then the assumptions you made when you built the code may be wrong, and you can at least see that you may be taking a risk, or at least go back and revisit the issue. But as far as more statistics for that about how many times do I see one of these funny things, does that mean a vulnerability? Well, it depends on context, like we just talked about with the defensive depth.
So given what you said about how open source code is so error prone, so has so many vulnerabilities in it, is there any methodology or best practices that you can offer to minimize or at least reduce the chance that this can happen as a result of all the libraries and components that open source relies on?
So a couple of things you might do. One is, as I mentioned, know what you're doing with the code. That if certain kinds of vulnerability exist because they're used in certain circumstances, let's make those graphics libraries. If this is all used internally, never leaves this room, probably your guy next door is not going to generate a bad gift and send it to you. We don't really care. That's sort of an operational view of what might happen. So that's one way. Second way is there are companies out there who will go and check individual components and will say, we've checked this one, we don't know of any known vulnerabilities in this one. So if you use their recommended repositories, you can at least avoid, again, these massive numbers of old stuff. The third thing, which people don't do very often but seems to be important, is keeping a detailed inventory of your use. That turns out to be tricky but important, because when something goes wrong, you need to be able to go back and fix it. And you can get the new version, but you have to find where all the old versions are. And a lot of old stuff is really a problem in this kind of environment. And again, we've done some studies for DHS on some of the home equipment, and it's, I suspect the routers in most of your homes are pretty easy targets if our data is any suggestion, because they're all filled with old code.
I'm just gonna add on, if you don't mind. On the dependency problem, it doesn't solve the issue, but at least the OWASP project dependency check, it's a top level project these days. It's written by Jeremy Long, who's a member of the Nova chapter. You can toss in a jar file, you can toss in a Java project, I think it's extended to .NET as well. It'll swing through, check through all of the dependencies, all the libraries that have been built in, try to identify them and compare them to known CVEs, and say, hey, you're using struts version something, this has a known CVE associated with it, you should probably update it. It doesn't solve the problem, but it at least can help out.
There's another approach that some companies are recommending. I don't have enough experience with them to offer an opinion on the validity. They call it RASP, Runtime Application Security, P stands for protection, something like that. But ignoring the acronyms, what it really amounts to is an application-specific firewall.
Yeah.
And so all the communication going in and out of an application is checked to see whether it's behaving in the way that you expect or not. And if it doesn't, then it turns it off. So it's a way to contain damage in those kinds of circumstances.
But don't you think a closed source image library is going to have a bunch of holes in it too? I mean, part of the problem is it's got to deal with the kernel all the time, right? So when you say that open source has more, open source software's got bugs in it.
Yeah.
But don't you think the closed source has bugs in it?
Sure. So, but two comments. The first one is because open source is so used that the same vulnerability is everywhere. And I mentioned the study about that old code seems to have more problems. The other issue that they found, which was not surprising at all, is that the more something is used, the more it's a target of attack. If I write my own program and I run on my own system, that's usually not a very interesting target for the guys in Romania. If everybody is using it, it becomes a lot more interesting.
Type services.
Yeah.
Easier, yeah.
They like reusable code too.
So there's a recent FCC rules they're asking for comment on where they want to make sure that the radio, all the software-defined radio portion is locked down so that when it's tested, it operates a certain way when it's tested, and they want to sign the code so that someone else can come in and modify the code and have the radio operate differently. So, but then you look at things like routers, right? And if you lock down the code in a router, and somebody couldn't figure out how to put, some of the open source router code on it, then you're gonna have the bugs, and they're gonna be there all the time, and nobody's gonna come along and fix them. Do you have any approach for dealing with these commodity things? It's not worth it for a company, right, to sell something for $50 to go back and maintain it for 15 years, right?
So we get back to the stuff that's already out in their field is just problematic, and don't have any magic answers to that. What I think is happening, and I say that only because it's happening to my TV and it's happening to my washer and my dryer, is that the companies are doing over-the-air software downloads. Tesla obviously does that as well. You can argue whether you think that's a good thing or a bad thing because they screw it up for everybody, right? But at least it's a approach that seems to be being employed more as a way to deal with it. I don't know anything about the software-defined radio regulations that you're talking about, so I don't know what that issue is. But we talk about the supply chain in the more general sense, especially if you're buying things from third-party vendors as opposed to just pulling them out of the ether. There's a process, a methodology called SPEEDO, and keep you covered. It's about supplier. Does the supplier that you're using know how to build secure software? Do they have these kinds of rules in place? If they don't know how to do it, then don't expect something good for them. Is the product that you got, the P from the actually secure? Do a scan on it. Much to my amazement, I've gotten reports of commercial software that people have done scans on that is scary. Third thing then is distribution, which is what you were alluding to, is between the time it left the person who built it and the time it comes to you, was it changed in any way? And I saw a demonstration from a employee security analyst where he took a calculator program and in less than 7 minutes turned it into a keyboard capture malware program. And I think it took him that long because it was at a conference he was demonstrating it to the audience. I think he could have done it a lot faster, but that's an issue as well. Is do you know how the software got into your hands? And the last one, which we talked about already, is the operational environment. After you've made your choices, you made it against a certain set of assumptions. If those assumptions change, then you've got to rethink whether the component you have makes sense or not. But the software-defined radio, I think, opens up a bigger problem, and this is yet another talk that I give. The catchphrase in that talk is software is the new hardware. That everything that used to be done with levers and pulleys and gears or whatever is all being done in software now. The Dreamliner is basically a computer wrapped in plastic. The military jets, 80 to 90% of all the function that's in them is done in software, not in hardware. An Air Force general once told us that it used to be that the way that he got an advantage over the adversaries was by bending metal better. Because now it's I have to program better. So that's how the world's moving. And software-defined radios is one particular example. I pointed out to people because software-defined radios are what's going in these things as well. The broadband processors in here have stopped being analog electronics. They started being basically digital signal processors. And what makes it scary from a security perspective is two things. First, that processor, just like there's two other processors in here. Okay, anyone know who the other two processors are? The ARM one, that whatever your application was, and the SIM card is actually a full job. They all have access to everything. You think that your program is getting a hold of your contacts or whatever. Well, that's shared memory. The broadband processor can get that too. Now, the SIM card you think has some sort of security, and the ARM you got to do some stuff. By design, the broadband processor has to work in an insecure environment. When this phone talks to a random tower, it doesn't know it's talking to Orange or Verizon or whatever. It's all in the open protocol where they all sort of exchange back and forth with each other until they get enough feeling good between the different vendors that then can allow you to have my Verizon cell phone talk to an AT&T tower. Well, you got everything happening out in the open. There's not a lot of security in there, and this thing has access to everything in there. It's a sort of it looks like a fascinating attack surface to go after in order to get into the phone. But as things move into software, that becomes a bigger and bigger issue.
What do you say about politics and ego in open source? And what I'm saying specifically is, let's say, take an example, OpenSSL. OpenSSL is chock full of vulnerabilities to the point that different developers forked it and made LibreSSL, okay, and fix those vulnerabilities. The problem is OpenSSL remains standard on most distributions because there are corner cases that they bring for their clients that opens up the company that makes themselves bring to clients. They want to maintain backward compatibility. Okay, these FIPS 140-2 compliance and LibreSSL dropped it. Okay, so, but again, this remains vulnerable and distribution remains vulnerable. What can be done about that?
I don't know. To be honest, there are some things we have ideas of how to fix. Other ones are, if you said, outside of the technical realm that I have any ability to make recommendations on. My team is clever, they're not yet. I do have a sociologist on my team, however, who does look at various other kinds of things. It's interesting, how does this stuff change if you have a different culture? It turns out that the way Indians attack and Chinese attack and Romanians attack and Americans attack, you look at the codes, it's different. But that's a whole other topic again.
Any other questions?
So quick question, go back. Which one is better quality, open source or non-open source?
Oh, God.
you mentioned open source had no problem, right? But is there similar comparable non-open source?
I don't know. I don't know if the data has been put together. And I suspect you may find the answer differs in time. There's an awful lot of old code, code that has years encoded in 2 digits. So lots of stuff around. I don't know.
With that, I'd like to thank Dr. Mark Sturman again. Again, keep an eye out on the meetup page for the December social with the Nova chapter. We're still trying to figure out the exact date. We're shooting for December 9th and at 4 Courts in Arlington. So that's the tentative plans. Just keep an eye on the meetup page for the definitive stuff. So thank you everyone for coming out.